So we're looking at an application of a line integral in that it can be used to find the area of a region. So if you notice in this little theorem we have here, if R is a plane region bounded by a piecewise smooth simple curve oriented counterclockwise, then the area of the integral is given of the region is given by the line integral. So great. That hypothesis there sets us up very well to be able to use Green's theorem as a means by which we can find the area of a region. But as a line integral, let's take a look. So notice that the area is the 1/2 the integral over the curve C of x dy minus y dx. Traditionally, we have been looking at line integrals as the integral over curve C of m dx plus n dy. But notice that in this case, we have the integral over curve C of x dy minus y dx. So we have to be careful. Remember that n is associated with the differential dy. So the n for this integral, line integral, is x. And the m is always associated with the differential for x. So our m in this instance is negative y. So let's go ahead and look at how we might use this. So here we want to consider setting up a line integral to find the area of the region R bounded by these curves. Now, as I look at these curves, the x equals 0, that's pretty straightforward. That's going to be along the y-axis. Let's take a look at these other two curves. So for this curve, this line, we could solve for y. And if I did that, I would get the line y equals 3 halves. Oh, I don't know why my 3 disappeared. 3 halves x. Pretty straightforward line with a slope of 3 halves, and it passes through the origin. And then this line, also pretty straightforward. I could solve for y, and y would equal, in that process, I'd get negative 2y, or 2y equals negative x plus 8. But when it's all said and done, I'd get negative 1/2 x plus 4. So I've got a region bounded by these 4 lines. So here I have a graph, and I have identified the curves that form the boundary of my region. So we're going to go ahead and graph those. So first of all, we have the line x equals 0. So that's along my x-axis, or my y-axis. I have the line y equals 3 halves x. So through the origin has a slope of 3 halves. So it's going to look something like this. That's my y equals 3 halves x. And then I have a line y equals 4 plus negative 1/2 x. So I have a y-intercept at 0, 4 and a slope of negative 1/2. So my third line looks like this. So y equals negative 1/2 x plus 4. Okay, so those are the boundaries. And in terms of the area of the region we're interested in, our region is, let's try this a little better. Our region is right here. That's the region we're interested in. So there's R. And remember that we had to have this boundary of a piecewise smooth curve. So here's my boundary. We'll call that curve 1. That's one side of my triangle. The second side of my triangle. And this third side of my triangle. And notice that the curve that we're talking about is basically the union of those 3. Okay? So our area is 1/2 integral along our curve of x dy minus y dx. So keep in mind that that's what we're trying to determine. Now, in practical terms, if I were to evaluate this as a line integral, then this area integral would have to be broken up into a sum of 3 different integrals. Each one of them I'd have to integrate along curve 1, along curve 2, and then along curve 3. Oh, and keep in mind that if I'm interested in applying Green's theorem, I need to make sure that this curve is oriented counterclockwise. So let me put that on there. Okay, so let's go back, and before we dive into the problem, let's think to ourselves, what are the pros and or cons of solving for the area of a region as a line integral? And then what other techniques might we be able to use to answer this same question? So let's go back and look at this. So if I wanted to do this as a line integral, let's think about what potential pros and cons there are for a line integral. So if we were to solve as a line integral, one of the pros, and probably the biggest pro for doing it as a line integral, is that it always works. It's like using the quadratic formula on any quadratic equation. It always works. May not be the most efficient or the easiest, but it will always work. In this instance, though, there are some cons, and probably the biggest con is that our curve is in 3 parts. So it's piecewise smooth, and each of those 3 parts are smooth. But I would have to do 3 parameterizations to be able to, parameterizations, I'm going to abbreviate there, to be able to compute the line integral. And so that's not a lot of fun. Can be done, but if we have alternatives, probably not the most efficient. So, with that in mind, before we dive in and say, oh, it's a line integral and I'm going to do it as a line integral, if I'm told I don't have to, and if I have other options, I should consider them. So let's look at other possible techniques. To consider. Now, these may work, they may not work, but I need to be aware they are available and then evaluate the possibility for each one. So, one possibility is the fundamental theorem for line integrals, FTLI. That's a possibility. Now, you'd have to go and evaluate whether it applies or not, but it is a possibility. The other possibility up to this point is maybe we can use Green's theorem. So let's go ahead and take a look at what that might look like in terms of Green's theorem. So here's our line integral for area. Notice that I've identified my m that accompanies the differential dx and my n that accompanies the differential dy. And now we're examining for the assumptions of Green's theorem. So recall what our region looked like. Okay, nice triangle in the plane. I could draw any number of regions, open regions that surround it, so no difficulty there. So the question is R simply connected? Yes, it is. R is a simply connected region. So yeah, we've got R is a simply connected region that is bounded by a piecewise smooth simple closed curve. That's the first hypothesis satisfied. The second hypothesis is about M and N and their partial derivatives being continuous in an open region containing R. Well, M and N are polynomials, which are wonderful types of functions because all of their partial derivatives are continuous. On any open region, continuous, I lost a U there, I think. On any open region, R in the xy plane. So we've satisfied the second hypothesis. So we're good to go. We can use Green's theorem. So the question that was posed was, could we use Green's theorem? And should it be applied, and why or why not? So yes, we could. Absolutely. And then the question is, should we? So yes, Green's theorem can be applied. Be applied. Okay. And should it? Yeah, it probably should. Because because a double integral is probably easier than 3 separate line integrals. Is likely easier to perform than 3 line integrals. And so if I were thinking about applying Green's theorem and actually going through the process, here's my area line integral, and here is Green's theorem. And notice that I've identified M as being negative y and N as being x. So my area would be, oops, I lost a 1/2 here. A 1/2 times the double integral over my region R. Partial of N with respect to x is 1, minus the partial of M with respect to y, negative 1, dA. So that would be, that's 2 times 1/2, so that would actually end up giving me a 1 double integral over R dA. And so we could use the trick that we used earlier. I know it's a triangle. I can do 1/2 area of base times height. But just in the case that you don't catch that or you don't think to do it, let's go back and just identify quickly what our limits of integration should be. So looking at our region here, if we were to draw in representative rectangles to try and describe our region, we would have to start our rectangles at x equals 0, and we would continue to represent those rectangles until we got to a value of x equals 2. So my limits for x are from 0 to 2. And then the bottom of the rectangles would be y equals 3/2 x. The top of the rectangles would be negative 1/2 x plus 4. So that would give me my limits of integration for y. So we'll go back and we'll put those into that area integral. So here we have the region that we found, our description, and now we've used them as our limits of integration in our area integral. And so we have the integral from 0 to 2, integral from 3/2 x to negative 1/2 x plus 4 of 1 dy dx. Again, If I recognize it as a simple geometric formula, I can go